Hey guys, it's Bo from Leet Code Answers. Today we're going to be going over one of my favorite problems called two-sum, and I'd recommend anybody watching that has not attempted this problem or seen it before to please try so on their own, as the only way to truly understand the algorithms I'll be talking about is to attempt it on your own. If you're still stuck, if you've tried it for a while, can't figure it out, you're in the right place. We'll be going over two different solutions. One will be a brute force algorithm, and the other is the eventual optimal solution for this problem. So go ahead and reading it here. We have given an array of integers called nums and an integer called target. Return indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. So in example 1 here, we have our nums array. It contains the numbers 2, 7, 11, and 15, and our target sum would be 9. It says our output here is 0 and 1 because the 0 index and the first index inside of nums both add up to 9. Some other constraints in this problem to consider is that the length of our nums array will always be greater than or equal to 2, but less than or equal to 10 to the fourth. And for all intents and purposes, any number inside of the nums array and any number that could be considered a target to sum up to can be any integer. When you see something like negative 10 to the ninth, less than or equal to nums, and then less than or equal to 10 to the ninth, basically that means any integer that a computer can process. Also, only one valid answer exists, and there will always be a valid answer inside of the nums array is what they are giving us. So let's go to the drawing board to truly understand this problem and maybe craft up a brute force solution. Alright then, so this problem is slightly modified from the one we looked at earlier, where our nums array is the same, but our target has now switched from 9 to 22. Taking a look at it at face value, it's pretty easy to see that the numbers 7 and 15 are the only ones inside of nums that can add up to 22, so we would want to return the indexes of 1 and 3. Starting to think, can we devise an algorithm that could do that for us? Intuition would say we would need one for loop looping through to check if one number added up to the target, and you would need an inner for loop to check if both numbers would add up to the target. So that's exactly what we're going to do here. We're going to have an outer for loop and an inner for loop, which is dependent on the outer for loop plus one index. And we'll talk a bit about why later. So right now we're going to be checking if 2 and 7 add up to 22. They do not, so we'll move our inner for loop an additional index over. And now we are checking if 2 and 11 add up to 22. Does not, so we move 1 over. Do 2 and 15 add up to 22? They do not, and instead of moving our inner for loop an additional index over, we'd get an index out of bounds exception. We're going to move our outer for loop 1 over, and our inner for loop will now go our outer for loop plus 1 again. If we needed to check the same index, we would want to start at the same place as our outer for loop. But the problem says we can't return the same index even if they do add up to the target number. So we're going to move one index over in our inner for loop. So now do 7 and 11 add up to 22? Does not, so we take our inner for loop over 1. Do 7 and 15 add up to 22? It does, and now we have our answer being the indices of 1 and 3. So thinking a bit about this problem more generally, let's say we had 100 inputs into our nums array, and the target we wanted to sum up to, the answer was the 98th index and the 99th index, all the way down at the end of our nums array. we would be checking every single element starting from 0 all the way up to 98 and 99 if they summed up to our target. And now that's a lot of calculations, looping through the entire array very slowly. And whenever you loop through an array multiple times based on an element before, that's going to be a complexity of O of n squared, a time complexity. This is generally a complexity you'll get with most brute force solutions, and it's generally the one you'll think of first. And the space complexity we have, we're not creating any more arrays or data structures that are dependent on the amount of size of an input or the amount of size of another array. It's a constant array we're creating, being two numbers for our output. So our space complexity is actually going to be O of 1, which is constant, which is great. So now let's take a look at what this type of algorithm would look like in some code. So this is our brute force algorithm we came up with. Using an outer for loop we'll call outer, and an inner for loop we'll call inner. The outer for loop starts at index 0, and our inner for loop is our outer for loop plus 1 index over. So taking this example here with nums being 3, 2, and 4, we want to find two numbers that add up to 6. So inside of this algorithm, we would start at index 0 and index 1. So 3 and 2, do they add up to target 6? They do not. So we move our inner for loop over. Do 3 and 4 add up to 6? Does not. So we'll move our outer for loop 1 over because we've reached the end of the inner for loop index. Now do 2 and 4 add up to 6? It does. And instead of returning the values 2 and 4, remember we want to return the indices that we found. So we would return the outer number and then our inner number. And at the end here, when we have a return new integer array of -1, -1, we're not really going to be reaching this. Inside of this problem, it says there's exactly one solution, which means there'll always be one solution inside of the array. But our compiler won't be happy with us if we don't have a return statement outside of our for loops. So we just need to put this here to make sure it compiles and runs correctly. So if we run the example here, we'll see that we have our correct output. It's running the first example of 2, 7, 11, and 15. We do expect the results of 0 and 1. So now we're going to submit our solution and see our runtime. So the runtime is about 28% faster than other solutions and 63% better than others in memory usage. So let's see if we can devise an algorithm that can maybe improve upon this and come up with a faster solution. So back to the drawing board here. Our O of n squared solution is passable, but we want to find a faster time complexity to find the sum of two numbers adding up to a target. So we have to get a bit creative here. And one way to do it is, instead of thinking about it as the sum of two numbers adding up to a target, we can think about it as the difference of the target minus the index we're currently checking. So for instance, if we had our target as 22, the difference of 22 and 2, being we're checking index 0 first, would be 20. Now, if 20 was inside of the array, we would know to return the index we had 2 at and the index we had 20 at. And there's a way to do this with a data structure called a hash map. Now, with the hash map, it's really great to use. It has based on key value pairs. So in this case, we'd have an integer being the number we're looking for, and an integer being the index where the key we're looking for, if it added up to that index, equaled our target. And we'll see that a bit later as we go through this example. Starting off here, we're going to take our target and the index value at index 0, which is 2. We're going to take 22 minus 2, and that makes our difference of 20. Now, if 20 is contained inside of the hash map, we have our answer, but is not. So instead of putting 20 in, we're actually going to put 2 in at index 0, so we can remember where the value is if we find a 20 later on inside of our hash map. We're going to move along here. We're now checking the difference of 22 minus 7, which is 15, at index 1. Is 15 contained inside of our hash map? It's not, so we'll take 7 and put it at index 1 as a key value pair inside of our hash map. So we're going to move the for loop over one additional index. Now we're checking target 22 minus 11 is also 11 at index 2. Is 11 contained inside of our hash map? It's not, so we'll put that in there at the second index. Finally here, we're going to move to our last index, 15. The difference between our target and the index we're checking is 7. Now, is 7 contained in our hash map? It actually is. So we're going to return the value of 7 inside the hash map, which is 1. And we're going to return the index where we found the difference between the target and the number, which is 3. So in that case, our output would be the same as 1 and 3. And the time complexity here, as compared to our other solution, is actually O of n. And the reason is we're only looping through the array once, checking each number individually each time. Now, while our time complexity went down, our space complexity actually increased from constant to linear. Reason being, our hash map is always going to be dependent on how many differences we need to check inside of the nums array. So in this case, we have 4 differences we're checking. We actually only needed to put 3 values inside the hash map because it was at the end of the index. But the worst case, if we had 100 numbers, it could be we have 99 values inside the hash map. So if a data structure we create is dependent on an input that we don't know, then it's going to be linear space complexity. And let's see what this solution would look like inside of some code. So this is our linear runtime solution. We're going to start by initializing a hash map at the top. We're going to name map. And we're going to have one for loop that will only loop through once through the array until we find our answer. And every time we're going to initialize a difference integer, which will take our target and subtract the number we're looking at inside of the array. And we're going to see if the map contains that difference. And if it does, we get the value inside of the map of that difference and return it with the value of our for loop, which should be the index that the difference pairs with to equal the sum of the target we're looking at. If it doesn't contain it, we store the number we're looking at in the array with the value at which index it's stored. So for the example down here, our difference would be 6 minus 3. And obviously it's not in our hash map because we just initialized it. So we put 3 and 0 inside of the map. Next we're checking 6 minus 2, which is 4 inside the hash map. It's not, so we put 2 and 1. Now 6 minus 4 is 2 inside of the hash map. It is, so we take the value of 2 inside the hash map, which is 1 here, and we return that with our outer for loop, which is also at index 2. So we would return the values 1 and 2 in this case. And like with the other solution, you'll never reach line 15 here, returning -1 and -1. If there wasn't a value inside of the hash map that would return 2 sums to the target, then you would reach the statement. But again, the problem says we will always have this. So we'll run our example here. We'll see that it returns 0 and 1 as it did before. And now we can submit our solution and check if the runtime is faster. And it is, so it's faster than 99.5% of online solutions, but our memory is a little bit more. Again, we went from constant time complexity to linear, but going from O of n squared to O of m time complexity is a lot better in the long run. So hopefully you guys found this informative. Thank you for watching, and I'll see you guys later.